Gents, welcome to Electrical and Electronic Power and Drive Systems. Level 6 module, as you know. Assessment's in 3 parts. You've got 2 assignments. Assignment 1, probably be issuing that next week. I can get it moderated in time. Okay. You're going to analyse and critically evaluate methods of AC and or DC motor control. So part of next week's session will be around me going through how induction motors work, for instance, and a little bit the week after about methods of control of motor, speed control and so on, with a view to showing you the kind of depth you need to research to be able to specify a motor for a given application. That's what you're going to be asked to do in the assignment. Yeah. So that'll then involve you going off and researching some other types of motors, how they work, what their characteristics are, so you can make an informed decision as to what motors you pick for your application. Yeah. Second assignment, which will happen as that one comes in, following week, issue the second one. The second one is kind of left for you to research in a way. If I keep it the same, and I'm not planning to change it, but I might change some of the applications that I give you as options. But you're given some options for different uses of power electronics. One of the ones I used last year was high voltage DC transmission of electricity, and the other one was induction heaters, using induction heat. So you'll then be expected to go out and research those topics, choosing one of them, and how the control of that power electronics is used to control those systems, and how useful they are or otherwise. Yeah. Most people picked the HVDC last year, by the way. In fact, I think all of them did, to be honest. Hi, Matt. And then the third part to the assessment is the 2-hour examination, late May. I've got a date for it, but I can't remember what it is off the top of my head. Alright? Carry out analysis of 3-phase power distribution systems. That's a little bit more than that, because I've got a question on transformers in there, star and delta systems, and load centers. And we'll be going through that work, the whole 10, 11 sessions before we start revision, and then there'll be all kind of revision sessions at the end, practice questions, and an example paper. Okay. Now, there is maths in this module. Okay. It's not particularly difficult maths in essence. Ohm's law, power, all that, and with complex numbers, which you've all hopefully met before at some point. But it's difficult to do and get that maths right if you don't understand the underlying electrical principles of these systems that we're going to be analysing. So star and delta connected, 3-phase systems and so on. Yep. So that is what the module is, and that's how it's going to be assessed. We aren't really doing anything towards the assignment work tonight. It's going to kind of introduce the module and the first bit of the calculation stuff. Okay, so the plan is to split the earlier lessons on the module into 2 parts. Part 1, analyse the power systems, the bit assessed in the exam. That don't necessarily mean we'll do it first in the session, but we're going to do some work every week on calcs towards the exam. The other half of the earlier sessions will be things like analysis of motors, the other uses of power electronics, the control systems. Yeah. Towards the end of the module, once you're working solidly on assignment 2, kind of from halfway onwards, the whole session will be towards doing the calcs and learning towards the exam. Having said that's a lot of calcs, we're also going to build in a little bit of practical experimentation. Not individual, but for instance, we're going to develop transformer so we could do an analysis. We're going to apply that analysis to the transformer on the rig. So that's kind of proven that that analysis works and gives you valid results for that transformer. All right. So although I'm going to put the circuit together, but we're going to take measurements from there, use them in calculations, and prove that that gives us the right. So, making a start. Power in single phase AC circuits. Okay. Now, a little bit of background. A single phase load supplied by an AC sinusoidal voltage. We specify instantaneous voltage and instantaneous currents with lowercase v and lowercase I. You have to be very particular here about that notation. So when you're handwriting in your exam scripts, kind of overemphasize lowercase v, uppercase v, so I can see that you're keeping to the right kind of notation. Alright? Because a lowercase v at time t is the instantaneous value of that waveform at an instant in time in seconds. Right, the form of that is Vm, so capital V, because we're talking about the peak voltage, the maximum voltage of that waveform, multiplied by the sine of omega t, so t is time in seconds, omega is the angular frequency in radians per second. If the frequency f is in hertz, then omega is equal to 2 pi f. And sometimes we'll be needing to know us that value, sometimes we'll be working with it as omega, but always in radians. So your calculator's going to need to be in radians when you're doing that. Okay, there is the odd time when we want to know what a phase angle is in degrees, we'll need to do a conversion. Alright, and then this bit on the end, plus or minus theta 1, that's the phase angle of that, reference to 0 phase. Same with the current, instantaneous value is the maximum or peak current multiplied by the sine of omega t. If that's produced by that voltage, then omega t must be the same, but the phase angle may or may not be different. The current and voltage may or may not be in phase. So there's some very early terms that you're going to have to get used to, and understanding that this is the standard form of a sinusoidal wave that could be representing either voltage or current. Yeah. Power in single phase AC circuits. Power is where things get a little bit tricky in AC circuits, unless all you've got is a resistive load. As soon as you've got a coil, as in the coil winding of a motor or a transformer, and or capacitance in the circuit, your current and voltage are no longer in phase, and you've got 3 different types of power, as we're going to talk about in a little while. Alright? So it follows from the earlier bit, the instantaneous power, P at time t, delivered to a load, is produced as a product of voltage and current. So that's the instantaneous voltage multiplied by the instantaneous current will give us, at any point, the instantaneous power. Yeah, all happy so far? Not too difficult. Right. Active power. So, this is the first one of our powers. Active power is the useful power that you can use. It will produce heat, light, rotation of a motor. It's measured in watts. Okay? It's produced when we have a resistive load and the current and the voltage. So there's the current I, that little phasor, and the other top of each other, but I've just shifted them out so you can see that there's two arrows there. This is E, the voltage, and we get a power that's also at the 0 angle. Left to right horizontal, this angle equals 0 radians or 0 degrees. Where the load is purely resistive, current and voltage are in phase, have the same angle, and all the power from the generator is converted into useful power. So we can calculate it from the generator voltage times the current squared times R, or the generator voltage squared divided by R. They're the three standard equations for power that you will have met before. Yeah? Everybody kind of remember that from somewhere else? Yeah? Note, for correct calculation of AC power, the values of EG and I are RMS values. Alright? So if we graph these, and I'm a bit annoyed about this projector because we can't hardly see anything in my slides. The blue one is voltage, the red one is the current, and the yellowy greeny looking one is power. Yeah? And as you can see, with resistive load only, voltage and current are in phase with each other. They both cross the 0 volts line in the same places, and therefore we get power curve. It's not flat, that's lumpy, instantaneous power, but it's all above the horizontal line. It's all useful power. Yeah? Again, everybody happy with that so far? Nothing too difficult so far. Nothing we ain't ever covered before. I wouldn't have thought. Right, now we come to start to think about something that's a little bit more tricky. Reactive power, inductive. So, we'll look at a circuit that's not possible for us to get precisely in real life, but one that's got purely inductance, no resistance, no capacitance. Now that can't happen in real life because an inductor is a coil of wire, and a coil of wire's got resistance. Okay, but if we imagine we could have an inductor that's pure, then we get current and voltage that are out of phase with each other, 90 degrees out of phase with each other. Yeah? Happy? And how do we remember which way these are? Anyone remember that word I use? Civil? Matt might not have seen it before because I hadn't taught him before. Right, but we use this word. Let's just do a new page. C-I-V-I-L. Inductive circuit. Voltage leads current. It's ahead of it in the word. Yeah? Capacitive circuit. Current leads voltage. Yeah? So that's a way to check. And I always say, when we're doing those calculations with both, with either inductive or capacitive circuits, you know that if a circuit's overall inductive, we should have current that lags the voltage. It's got a negative angle. Because we could equally say current lags voltage over here, Or we could equally say voltage lags current over this side. Yeah? There's a way to check that you've got all the signs right in your calculations. Because if you know that's an inductive circuit, but you get a current that leads the voltage, you're gone wrong somewhere, you missed a negative sign out somewhere. Yeah? The difficulty comes when you've got both capacitors and inductors in the circuit, but the circuit is still overall either capacitive or inductive, depending on which one's got the bigger push in it. Alright, and we'll come across generally circuits, main circuits, power circuits are generally on the inductive side. Capacitors used to bring power factor back, which is another subject we'll be touching on at some point. Alright? So that's a little check for you. Anyway, in this circuit, are we looking at civil? We've got an inductive circuit, and I've shown that the voltage is ahead of the current, 90 degrees ahead. So I've done it the right way. Yeah? What we get is, when a load is purely inductive, the current lags the voltage by 90 degrees. The inductor is said to absorb reactive power from the source. Reactive power is measured in VAR, V-A-R, short for volt amps reactive. If we plot the voltage, it's the red one, it peaks, sorry, the voltage is the one, peaks before the current, which is the red one, 90 degrees before it. Look at the power waveform now. Half of it is above the line. Inductor's putting power into the system, but the other half, below the line, inductor's taking power away from the system. The net power used by a purely inductive circuit is nothing. You're magnetising the inductor, 1/2 cycle, demagnetising it the next half cycle. And you'd be doing that all the while, you'd be doing no useful work whatsoever. Okay? So the waveform shows each positive power pulse is matched by a negative one. No electrical power is converted to useful power. Inductive loads are said to absorb reactive power, QL, from the source. So we use Q to represent reactive power. We can have QL, inductive reactive power, and QC, the capacitive reactive power. Alright? Still no problems so far. Good. Goody, goody, goody. Let's skip over my fill one. Now, we've got... Oh, I've just done that. Oh, hang on. No, we are still... Okay, so, this reactive power absorbed by the inductor QL can be found as follows. Again, 3 ways to find QL. The generator voltage times the inductor current. The inductor current squared times the inductive reactance, where XL is equal to either omega L or 2 pi times the frequency times L, depending on what we know. Okay, or we can get it from the generator voltage squared divided by XL. That is if the inductor is directly connected to that voltage. If there's a series circuit, you'd be using the voltage across just the inductor. Yeah? Alright? You need to get used to these phasor diagrams, making sure you're confident which way round they should be, and so on. Alright? And we won't get anything wrong. Right, reactive power, capacitive. So if we put just capacitance in our circuit, and again, can't really be done, because the wires that go with the plates on the capacitor have got resistance and so on. Right, but imagine if we could, we'd end up where the current leads the voltage by 90 degrees. So this time, here's E, and there's I, and we talk about a positive being, or head being anti-clockwise around the rotation, and therefore showing that current leads the voltage. The capacitor is said to supply reactive power to the source. Alright? So, if we then, reactive power again, measured in VAR, volt amps reactive, but this time the blue peak is after the red peak, showing voltages lag and current. But again, we've got a half of a power waveform that's above the line and the other half is below. So again, no useful power. We've got, if we had just an inductor and a capacitor, we'd have the power shunting between the two, because in one half cycle the inductor will be losing its magnetism and charging the capacitor up, and in the other half cycle vice versa. You have a current flowing backwards and forwards between the two effectively. Not quite achievable, but you can get close to it. You won't be doing anything useful except making inductors and capacitors hot. Alright? Any questions so far on that bit? On that up to there? So we've got two different sorts of power at the moment. Real power, P, measured in watts. And we've got this reactive power, seemingly useless. Isn't. Because to go round, we've got to magnetise them. For our transformers to work, we've got to magnetise them, so it's useful. Alright? And we've got two different types of reactive power. We've got capacitive, inductive, and they're both measured in VAR, volt amps reactive. Again, we can calculate Q in terms of QC by the voltage multiplied by the capacitance current. Capacitive current squared multiplied by the capacitive reactance, which is either 1 over omega c or 1 over 2 pi fc. Capacitance is in farads. Or we can do generate a voltage squared over the capacitive reactance. Yeah. The other thing you must always remember about XL and XC, that's equal to omega times L, and that one's equal to 1 over omega times C. So as frequency changes, one of them increases in value, the other one must decrease in value, and vice versa. Yep. So that, whereas resistance has no involvement with frequency, reactance is a quantity that varies with frequency. But as soon as frequencies change, you've got to recalculate your reactances. Distinction between active and reactive power. You can't convert one into the other. They function independently of each other. Yeah. They can be treated as separate quantities in electrical circuits, so you can keep each of them separately, and then we can also calculate how they combine. More about that in a minute. They both place a burden on the transmission line that carries them, i.e. they both produce a current. So although these reactive power, capacitive and inductive, don't do any real work for you. They still draw a current. So they are a burden on the transmission line, the generator, and the steam system that's powering the generator. Yeah. Active power produces a tangible result in the form of work done, heat, mechanical power, light, etc. Reactive power does no useful work. It represents energy that oscillates backwards and forwards for magnetising and charging current. Okay. Large system, such as a factory, presents a large active reactive load in the form of heaters, motors, transformers, etc. They draw reactive loads to sustain the magnetic fields involved with them in the transformers, as well as active load to provide heat and mechanical energy. This leads to us to consider loads that absorb both active and reactive power. Yeah. And how we go about reducing the effect on the transmission system as well, we're going to study. Okay. So, what happens when we combine real and reactive power? So in our circuit now, we've got both resistance and inductance. And we've got two currents because they're in parallel. So we've got an inductive current down here. Sorry, a resistive current IR there, an inductive current IL there. Okay, there's the resistive current in the phasor diagram. There's the inductive current. CIVIL, lagging, got it lagging. Okay, that gives me an overall current for that circuit, because I can resolve those phasors, inductive current, resistive current, to get an overall current phasor down there at that angle. Yeah. And I also can say I've got power that's horizontal, and I've got QL in var that's vertically upwards. Alright. The current IR is in phase with the supply with the source voltage, whilst IL lags by 90 degrees. Current drawn from the source lags the supply voltage. So the overall current is behind or lagging the voltage. Not by as much as the inductor current, but it's still lagging. So this current. When we graph that, we find that we got a portion of active power above the line, and we got a portion of reactive power that's doing no work below the line. Yeah. Again, all reasonably happy with that one, that part. Good. Real and reactive power combined. Further, the magnitude of the current I drawn from the source can be found from this triangle using Pythagoras theorem, because we've got IR down one side, IL down the other side, so the overall current, the line current flowing, is the square root of IR squared plus IL squared. So there's a fair bit of Pythagoras theorem in this, using that to get results. Magnitude of the angle, theta, depends on the the value of the inductor, because if and the frequency actually. Although on main systems that doesn't tend to change very much, as you all know, Christian. I can't remember what the plus and minus tolerance on frequency is, but it's not very much, is it? It's not even a hertz, is it? Yeah. Alright, so the value of inductor will obviously change XL, which will mean that angle either narrows or gets bigger. Alright? Consequently, the larger the angle, the greater the current required to produce a given amount of real power. Because if we change the inductance in the circuit so it's bigger, this line is going to come down here. Yeah, because we got a bigger inductive current. It's going to bring this in here. Resistance doesn't change. That line becomes a steeper angle downwards and the length of it is longer. So we're going to be drawing more current from our supply. But we ain't going to do any more useful work. If we go back to our diagram, we'd have a bigger portion underneath than we had on top on the power curve. Alright? So, this greater current produces the same amount of real power dissipated in the resistor. More about that shortly. Alright? Also, our lines have got to carry more current, so they might need to be bigger, and so on and so on. So, real, reactive, and apparent power. So, we've got these two powers that we talked about. P, the real, Q, the reactive. They also resolve into a triangle, a power triangle. And on the hypotenuse of that right angle triangle, we get the value S, which is the apparent power for that circuit involving both active and reactive power. S is measured in VA, volt amperes. Alright, it's quite typical for AC loads to be rated in VA. Transformers are rated in VA. Yeah, and that's because they're inductive. We can calculate S from the supply voltage multiplied by the line current. Yeah, and from the power triangle, S is equal to the real power squared multiplied by the active power squared. So again, Pythagoras' theorem is going to come into these calculations around the different powers in a circuit. We're going to be doing some soon. So, expressed in volt amperes, VA, apparent power S forms a triangle with the real power P, theta, that is the same as the angle of the lagging current produced by the circuit discussed earlier. So, that angle in there, if we're talking about the same circuit, this angle, theta in here, is the same as the angle between the voltage and the current. Yep. Still all reasonably happy with that so far, yeah? Good. Okay, reactive loads and power factor. Any reactive loads on the system that require reactive power Q to set up magnetic fields, motors, transformers are typical ones. Heaters, Weldon plant. Okay. High reactive load Q means that supply lines have to carry more current at a given voltage to provide a given amount of usable power. Yeah, so that's that situation on the left there, where reactive load means that this ratio between the real power P and the apparent power S. That's why it's the adjacent side and the hypotenuse. Yeah? So any way that you can get the cosine of that angle will give you the power factor. Power factor is equal to theta. Yeah? Now, as you can imagine, the supply authority, and I expect Christian will back me up on this, don't like low power factor, because it means their cables have to be bigger, they get hotter, and they waste more energy, because they get getting hotter, they use more power in their own resistance. So for a given amount of power transmitted, cables would have to be that much bigger. So, if I remember rightly, implications, there we go, implications of lower power factor. Transmission line can only carry a finite amount of current. So they put these cables in, they're a certain size, and they can carry so many amps. Because a low power factor results in more current being needed to produce a given amount of useful power, it means that less useful energy will be transmitted by that line. This leads to supply companies that own the transmission lines penalising consumers for poor power factor through their electricity tariffs. So, as far as I know, and I don't know if it's any different, they do that by measuring what's called their maximum demand. Their maximum demand of apparent power in VA, and basing the electricity price upon that. 3 monthly, I think it used to be. Because I know when I was at Feb Wk, we used to go in once a week and check what the maximum demand meter had gone up to. There might be more sophisticated ways of doing it now. I don't know. You might be able to help with that, Christian, or not. Do they? Yeah, do they still penalise people with bad power factor? Do you know, or no? Well, there needs to be an incentive to spend the money installing all that power factor correction. So there must be a way somehow. But that's the basis of it. That you don't want poor power factor because you have to make your cables bigger, etc., and you're going to lose more in heat in the cable. Yep. And I found this, I don't know how old it is, but maximum demand charge. For each kilovolt ampere of maximum demand, so on 11 kV made each month, they'll charge so much for every kilo kVA. So if your maximum demand is up, and the old meter we used to have used to be an arm that pushes it up and leaves it there, so if it falls away again, you then months of very high maximum demand because of it. So he weren't very happy. But there you go, that's what you get for trying to buck the system, as they say. Ain't it for the night? Right, I thought we had some example questions, but let's have a... What we got here, I'll have a look in a minute. Let's just stop there. So that's the problem. And it says, calculate A, the in phase and out of phase components of current, IP and IQ. So we've got this motor connected. We know we're going to have 230 volts. We're going to have an IP and we're going to have an IQ. It's 90 degrees out of phase. How can we calculate those two currents? A. Yep. Yep. Because P is equal to, wait a minute, P is equal to E times IR. IP, sorry, the real in this case. Yep, so we can rearrange that to IP is equal to P over E. 1400 over 230 and whatever that equals. Is that what it says on my piece of paper? Yeah? And then Q is equal to E times the reactive current. Yeah? Therefore, the reactive current IQ is equal to Q over E, which is the 720 over 230 and whatever that equals. Yeah. check it, because I have been known to get them wrong. Yeah? Is that what come out to? Good. Right. B is, what is the line current? So, what we're saying here is, here's our generator. There's our motor. What is the overall current flowing? The combination of these two. How are we going to calculate that? Yeah, it's because it is this current in here, that one. So we can get it using Pythagoras. So there's a B. We can draw this triangle if that helps us. We've got 3.13 amps, reactive current 6.09 amps, IR. The line current is that one along there. Yeah. So IL is equal to IR squared plus IQ squared, all square rooted. And the result of that should be 6.85 amps. But push the button and check it, please. Yeah? Right. There are two ways that we could get the reactive power, the apparent power supplied by the source. Which way would you choose? S. Yeah. Yeah, because they're being given. So the ultimate way here is, because you're being given P and Q, put them on, express them in the triangle and use Pythagoras theorem because they're given values. The other way would be to use this line current multiplied by the voltage. Yeah. So here's our triangle, P, Q, which have been given in the question. We want to know S. So S is equal to the square root of P squared plus Q squared. That's equal to 1400 squared plus 720 squared. Push the buttons. You should get 1576 var VA, sorry. Whatever. Close enough. And then the angle could come from either of the triangles. Remember, it's the same in both of them. If you're interested in this angle here, how can we calculate that? And the result is given in degrees. What would be the absolute best way to do it? Considering the information given in the question. Remember, you've been given V and you've been given P and Q. So they're given values. So if we can use them, that would be the best way to go. Yeah. So what? Opposite side, adjacent side. Which ratio? Yes. Sine is opposite hypotenuse. Cosine is adjacent hypotenuse. Tangent is opposite adjacent. So we can say, we call that angle theta. The tangent of theta is equal to P over Q. Yeah. So the angle theta is equal to tan to the minus 1 of P over Q. Whoa, not P over Q, Q over P. Michael. I spotted my own deliberate mistake there. $720 over 1400 equals, and you should get 27.2 degrees, more or less. Okay, so that's one. Yeah. So have a go working your way through the rest of them. We won't get to necessarily do all of these questions every week. There may not be time. Okay. What I will be doing once I get set up with the website for this year, I usually put stuff like the videos. I will post handouts, PDF copies of the slides that I've scribbled all over. The videos linked into YouTube, and these sheets plus a work solution if I've got one. Alright, so everything is there then for you to go back to if you need to at some later point. Alright? So have a go. I'm here to help if need be.